Hello, everybody. So welcome to this conversation on timber event. I'm really happy to host here tonight Gianni Botsford and Cristopher Robeller that will both speak about some of the realizations, some of the work they have done with timber, and then we'll answer your question if you have some. It would be very interesting project to see on different usage of timber, because as you know, usually timber is used in the classical way to create timber frame, but here especially I invited Gianni and Cristopher because they are working on different type of design using shell or using design edit computer edit design to create timber structure. So it's really interesting to see different type of structures that can be done with timber. So thanks a lot, Gianni and Cristopher, to be here tonight. And thanks a lot to share your time and your work with the students that are here. So Gianni will start with its presentation about using timber in a local project as a local material and adapted the local architecture to modern, let's say, contemporaneous building, modern needs for buildings. So Gianni, please, we are listening to you.
Thank you, Mathieu. That's very nice of you. Thanks for inviting me. I thought what I would do is show two projects, one that's, I'd say, more kind of analog and one that's more digital, both timber. Let's start just explaining a bit about the practice and how we work. And the way we work revolves around the kind of concept of local adaptation, which is mimicking nature in an architecture that locally adapts to climate, culture, and context. Always been very interested in natural systems, especially sunlight, and a lot of the work revolves around that kind of interest. And understanding how organization of cities and vernacular architecture has evolved through an understanding of sunlight. If you look at a city like Marrakesh, where you have courtyards and very narrow passageways between buildings, primarily to generate a way of protecting yourself from the sun and keeping cool. And then culturally looking at how different people adapt to this issue. So on the image on the left is in London, where everybody's sitting in the sun. That's what we want to do here. On the right is an image in Washington, where everybody's sitting in the shade. It's a very simple kind of binary difference, but it's quite fundamental to how you approach architecture often in different locations. So I studied at the AA with Professor John Fraser in the mid-90s. He was a very early pioneer of use of computers in architecture, having worked with them since the 70s. And my diploma project was actually what you're looking at now, which is a computer program written in Lisp, Auto Lisp, which generated form and organization based on solar criteria. So this was something I'd never done, and I would say is kind of quite early work in using computers 25 years ago in architecture. Pre-Grasshopper, pre the kind of more straightforward ways we have now of using computers and coding. This, is extremely difficult for me to do, and it's not saying I'm a natural coder at all, but it made me understand what criteria are really important in architecture. And I took that with me in the work we've done. What that program did initially was take a point in space and understand the differences across the planet, which would vary hugely depending on where you are. It started to become something much more three-dimensional. And as more rules got added in, it became more complex. The forms became more complex. So looking at the first project, which I'd say is the more kind of analog project in Costa Rica, which is a climate that's very hot, very humid, huge amount of rain, quite breezy, quite windy. And the project's on a beach, facing a beach, surrounded by very mature trees all around you. Costa Rica has got a lot of national parks and is very kind of lush landscape. And what I went to do initially was kind of try to understand the culture there. So this was a house we visited where the guy would sit on the chair looking out of the window with his cigarettes. And at the end of the day, he'd close these windows, which initially I thought were windows, but it turns out don't have glass and don't have mesh in them. So they're very open to the atmosphere. And at the same time, buildings are built in kind of quite an ad hoc way. And I was really fascinated by this kind of 8-way connection that was just kind of put together very simply by the local tradesmen, using so very local materials for the roof, very local materials for the structure itself. So we started by analyzing the site for sunlight using Ecotect, and initially we had assumed that the kind of tree canopy would do a lot of the work of shading the site for us. As we kind of looked into it further, we realized it wouldn't do enough, and we'd have to do that with our building, and started to look at how you would self-shade. This is literally a square meter on the ground. What form would be needed to self-shade a square meter on the ground? This is another attempt at that using a different technique. What we came to eventually was a twisted parallelogram that was open to the sea on one end and open to the jungle on the other, but very carefully formed to protect the building from sunlight. The two facades are glazed facades from sunlight so that you wouldn't get overheating. So the site is existing house, and on the right to the east you have another house, and to the west you have another house. You're facing the sea, and the sun is very overhead. And so the site we decided on was between trees, as we couldn't cut any trees down. And this twisted parallelogram emerged through that process that did a number of other things, as well as being very protected from sunlight. So creating privacy with the solid sides and open views to the sea and the jungle. So that house is made of two elements: the main living space facing the sea and a bedroom facing the jungle, very open to the breeze, which is towards the sea, with kind of open louvered facade. And the two buildings pulled apart to be out of each other's wind shadow and lifted up off the ground. And built using very local materials. So this was a kachar, which is a very heavy timber that doesn't float, which we use for the foundations, and laurel, which is locally available, but it turns out wasn't available in the scale we needed, which was quite unusual. We had beams up to 10 meters. So again, going back to the kind of analog idea, we'd produced a lot of drawings and sent them over, but they just were not able to understand them properly. And we realized we had to physically make models. And I took this model to Costa Rica and said, I would like this building built a lot bigger, and kind of pointed to the site and literally explained that what they build here on the model at a bigger scale is exactly what the building needs to be. So these models were used to help that process, but I think a really fundamental part of that was to make a number of models of each junction, because they were surprisingly complex as you kind of work through the catalogue of them. So they could also refer back to these when they were building at full scale. So the site starts off with putting the timber piles into the ground, which are cast in. So you can just see them there being set out. And then the superstructure emerges out of the ground. And one thing I really enjoy with this photograph is that there's very little evidence of construction. There's no damage to the ground. It's touching the ground very, very lightly. And, you know, timber's a very versatile, relatively light material that you can work easily in different conditions without having a lot of other infrastructure to make that possible. And then the timber structure was lined externally and insulated externally and waterproofed with the galvanized tin. So here you see the house nestled amongst the trees. We weren't allowed to cut any trees down, not purely because of kind of rules, but the client just wanted to find a way to make it work in that way. And you can see the form has been generated very specifically to protect itself from the sun at all times, and the facades, the glazed facades, to be never to hit direct sunlight. The structure is essentially you could argue structural bookcases. We had to house 16,000 books in the house. And these went from 4.5 meters high to about 3 meters towards the back. And the timber beams running across the building are about 10 meters length. There's a louvered, locally produced louvered glazed facade system that we use with sliding doors, so you can completely open the facade when you want to and let the breezes run through. So the whole building was kind of naturally cooled and naturally controlled by the protection from the sun. And these large overhanging parts of the building, again, you could sit out, be protected, but it again shows how the glass is protected. And then to the rear was a bedroom wing that had quite a different atmosphere, using the same structural system, but facing the jungle with a more kind of calm feeling to it. So in London, then we built a house soon after that, or started designing a house soon after that. We didn't build it for a while. This is a kind of anomaly in London where there was a bungalow built in the 1960s and a back garden. So it's surrounded and overshadowed by a number of buildings, 5 stories. There's a very large plane tree. So it's north facing, and it goes against all the rules of what you want living in the UK. You don't want a north facing house. You don't want a north facing garden if you can help it. So again, we did solar analysis to try and understand it better, and then looked at breaking up that information vertically. So this is slicing every meter and doing the same analysis to try and work out where there are differences on this plot of land between good light and what less good light. Is very overshadowed. So there's the very large tree, as I mentioned, but we start to see emerging as you rise up 2 areas where there's better level of sunlight during the year. These are annual programs. So we are identifying really where could we put gardens that we could be looking into that would be sunny. And the idea emerged of an oculus, a big skylight towards the rear and to the middle that you show on the plan here. And this form emerged through that process, which is very, very specific to that analysis we made and to the site and the context. So it deals with the tree, the curvature deals with the tree, it deals with views from neighbors that need to have long views, and it deals with positioning of the oculus that had to be as high as possible without constraining any of the neighbors in order to get this light to come in. So the process went from then a kind of manual process of making models to a digital process where we started to build the model completely in Grasshopper. And there are quite a few issues that Grasshopper were able to tackle for us, partly to do with mimicking the physical models we'd made with mesh relaxation techniques and so on, but also partly to do with providing information for the structure and the spans and how close everything went together and so on. So once that model had been built, it could generate also the cladding pattern for the copper roof and the internal structural design of this superstructure. So the model just became more and more sophisticated for us, which is an incredibly useful process. And then you feed it through to the structural engineers who use it as well. And then the fabricators who we started to talk to. So this is the first fabricator we discussed this with and mocked it up to a kind of significant level. They were generating the beams using strips of plywood, interlocking with each other, which was a kind of different to our expectations, but an interesting solution we felt. And they mocked up the whole roof in their workshop at 1-to-1 to test this principle. And we developed a scheme with them quite considerably. And when you start looking at the drawings, you see how the complexity arises from the kind of differences we allow to happen in the form. So the 2 angles are not the same. The oculus is not in the middle, and those kind of simple moves that we wanted to stick to actually make the project much more complex. Because often you with digital techniques, you're trying to simplify it in a way, but in this case, we were kind of trying to do the opposite. So you can see the complex form in all these drawings that were generated by the fabricator. So the problem we had is this was about a year's work. And at this point, the timber fabricator went bankrupt. And we had to start all over again with another supplier. And fabricators are interesting, I find, because they have their own ideas about how things should be made. So we went then to a German company called Zublin, who said they would do it in glulam timber. So all solid beams throughout, but they're very complex beams. So if you start looking at their drawings, this is a kind of catalogue of the 30 rafters. They're all subtly different to each other, some kind of a lot more than others. But if you look at these drawings, there's the top view, the side view, and the end view of these beams. And each one, this again taken from our 3D model directly, has these kind of incredible differences and complexities to them. But again, they decided that the glulam was the solution, and they had to find a way to make them from this 3D model or from the drawings they produced, which then they surprisingly subcontracted to a company in Italy, who then made it again in a slightly different way to how we and the German company were expecting. I'll get to the end of these in a second. So here we are in the factory in Italy, where what they've done actually to make these forms is take our 3D model and loft it, the drawings onto the floor to work out exact dimensions of everything. And they did this not only to mock it up at full size, but also to make the components. So you'll see here they're making one of the glulam beams, and on the floor you can just see the plots of each piece that they've made to set up the jig for each mold. So the glulam beams are made once and then sliced and then made again to get the 3 different curvatures, because it's curving on plan, on section, and on elevation. And then these parts were then delivered to site and craned in. So I think there's 12 different sections that were prefabricated and lowered onto the site, which was meant as a very quick operation on site itself. You can see one of the sections being lowered. So the radial beams connect these elements. So they leave out every third one, they leave out the radial element, and that gets fixed later. And the 12 sections are lowered in and propped up temporarily, and then fixed once everything is connected together. And there's a satisfying moment in a second where it actually just fits properly. It's all made of spruce, and it had a coating on it, a protective coating, and also kind of white colored coating. Then the outside had a slightly different structure because the form was different, and then clad using actually quite kind of boat building techniques to make that possible, to get the curvature to work. And then interestingly, even the 3D, the grasshopper model was used to generate pattern pieces for the roofing contractor at 1-to-1. So we made the script on the right and then printed out each piece for the roofer, printed them out, and then helped them apply them to the roof to get the complex geometry to work. You can see the copper going in now. So the site is this site hidden actually behind rows of houses. You don't see it at all. Surrounded by gardens and then by kind of higher buildings on either side. And on the ground floor, you see the 2 gardens that create the light wells. that the space looks out into. And the whole building is essentially built in the shadow. So we built the house where there is no light, and we look out to where there is light, and we look up to where there is light. And in the section, you can see the position of the skylight, why it's so important to be where it is. It also goes underground 2 floors, and the light wells serve to bring light into the lower floors. And here you see the roof in the context. And then here you kind of see how that form has been generated very specifically by what is around it. In this country, there's a lot of conversation about contextualism, and to me, context is responding to these things rather than mimicking them. So I find it interesting looking at this, how it's different to what's around it, yet for me, it could only have been from this place. So the oculus you see in this little time lapse shows how the sun is just penetrating that part of the site, and how the oculus itself is capturing that light and bringing it in to the building. And if it had been any other location, it might not have been as optimal, and that was very important to get that to work. And then some views of the house. So this is looking from the western facing garden, looking back in, and then looking up at the oculus, which is always different. Every time you look at it, the light is doing something different within it. And I think it's quite something you're kind of visually attracted to. This is that rare moment when you finish a project where you can actually spend some time enjoying it and looking up through the oculus and experiencing the light and the changes before it gets occupied. But you can see that what was, from our point of view, in a site that was a kind of not a positive space, has created something very positive, looking up and looking out. And how the timber structure itself, I think, contributes to that in a number of ways, but I mean quite powerfully, the sense of movement, the sense of light, the sense of structure that are all within timber, obviously contributing to the sustainability question of what materials to build with. But we find that expressing the structure in the architecture is a very elegant way of making things work, and a kind of simple diagram that's legible within it. We use copper in some of the other materials, like internally for the kitchen, and timber also for the structural staircase and lining of some of the rooms in the lowest floor, or in the lower floors. This is another time lapse that just shows from the inside what the kind of project in my mind is all about, which is this view up to the sky and the changing light conditions, not only during the day, but also at night. I mean, you'll see in a second, you actually see the stars and experience clouds, movement, and this different weather, which is, you know, a connection to nature that is always something one wants to have. And I think this kind of move of creating a building that looks up to the sky through an oculus has made that happen. And I'm always just surprised by how many differences there are, and how much movement there is, and how many changes there are that you experience, partly just because of the light, but also I think the structure itself helps exaggerate that, almost becoming a kind of measure of what's around it. So thank you very much. Those are my 2 projects I want to share with you, and I'll hand over to Cristopher.
Okay, thanks a lot, Gianni. It was really, really nice project to share, and really nice approach, explaining how you decide on the design of the building according to the light, especially according to the light, was really good to see and to share with us. So thanks a lot again.
Thank you.
We will be able to have a question and answer session at the end of the presentation. So now I will ask Cristopher to continue to share with us his project and how he designed or he participated to the design to very different buildings. That's what we have seen, but again, using parametric design, computer-aided design to create timber structure. Please, Cristopher, we are listening to you.
Yeah, I think we're coming from a very similar direction, even having spent time around the Architectural Association, having spent time and studied in London, which is such an amazing creative hub. And yeah, I'm a huge fan of Gianni's work. I have to say that. Great presentation. Thank you. So I come with my questions at the end. So let me try and share my screen. Is that working? I cannot see you anymore, but you can see me, you can hear me, and you can see my screen, hopefully.
Yes, we can see your screen, no problem.
Okay, great. So yes, thanks for the invitation. I'm showing images that are from my time at various research institutions. What you see here is the current lab, which is at the Technical University of Kaiserslautern. And what can we do in the university? We cannot really build buildings, but we can typically make prototype structures where we just try to explore the possibilities of technology. I think we have quite amazing technology out there. And I think it's important that we keep trying new things and going new ways with this technology. Because ultimately, technology has always had a great influence on architecture. And it's really always been much influenced by the tools that we've been using. You see here the hand tools in the beginning, later on the machine tools, which were taking on the power of processing. And then now the latest generation, the information tool technology, which is really taking parts of the information processing and the thinking in this fabrication process. So these tools have an influence on the way we build, and they have, for example, a very obvious influence on joining techniques. And you see that in traditional timber structures, you had very much form-fitting joints using geometry. And then when industrialization came along, much of this was actually thrown overboard because we were not able to do such complex joints with the machines that we had, right? We had presses that can make these steel joints, right? They can mass produce them. Everything was about mass production. And I think now what's happening is we're going back because we are now much more capable with the technology that we have. We can do complicated things, and that means we can go back to taking advantage of geometry. And this is really something very important to understand, that if you look at nature, and I'm a huge fan of nature, just like people like Frei Otto, you see the ingenuity of nature really using form to save material and to be efficient and to be lightweight. And I think we're far from understanding what's going on there and really taking advantage of it. But I find it still very inspiring. And it's very much the same that we see here going on with these collections. So, for example, this is a new interpretation of such a joint, and it's for different reasons. We're now doing it for fabrication, for prefabrication, right? I mean, we can actually use technology off-site, which right now we do not have on-site because the robots on the building site, which is a messy place with the weather and rain, it's going to take some time. We will have the robots on site, but not now. Now we have the robots in a factory, and so we can actually take some of the assembly and put it into the factory, and the last step that's done on site, we try to make it as easy, as error-proof, and as quick as we can. And this joint here is doing nothing more than a traditional wedge joint, which is pretty much transforming a force of inserting this joint into pulling together two plates, but it's done entirely without steel. Steel screw would do a similar thing, but here we do it with hardwood. We do it with beech wood, which is particularly important because here in our forests, this is a wood that we haven't been really using for buildings. We have created monocultures because we've only been using one kind of wood. And so this is actually a step in the right direction to really try to understand the diversity of the forest and use different woods for different purposes. So I'm going through 3 projects, and the first one that I'm showing is the VD Theater. And we're coming back to this idea of geometry, which is so often used by nature to make things efficient, to make structures efficient, to make them lightweight. And this is one way to go about such a design, to start with a lightweight overall shape. And there has been a lot of experimentation, as you see here in the 60s and 70s, with folded plates when they were moving from concrete to fiber reinforced plastics. And fantastic creative work, actually, but didn't catch on building with plastics since it's a difficult building material. And plates, as we have them now, they weren't really timber plates. They weren't really available at this time. So this first project, it was really trying to explore the possibilities of doing such a structure with timber. And as you can imagine, the joints, they play a big role in this, especially if you join one plate with multiple other plates at the same time. There are some challenges, and this was largely the work of my PhD thesis, to explain a little bit and understand how this works and what you can do with it. Hollow structures, because if you can make these very thin joints where it's really difficult to put in a screw, right, because you have to have side distances, etc. And once you can get around that problem, you can actually make multiple layers of thin materials and save a lot of weight compared to one thick plate. So the idea here was to make these corners, which we have in a folded structure, and to use double through tenon joints. And there was a lot of playing around with little laser cut models, just to understand how you can also use this phenomenon of interlocking, mutual interlocking of parts to strengthen the structure without using any steel fasteners. But yeah, I mean, it gets really interesting once you take it to a building scale, because making little models is one thing, but really making a building is a completely different story. So that was a fantastic opportunity for this VD Theater project to really take it to full building scale. And in this case, it meant 5 centimeter thick wood plates, CLT. And this was the first prototype that we made. And you can imagine that you have some certain imprecision of a few millimeters, but you do not want the joints to lose contact. So this is why they are protruding. And this is just what the joint wanted to be. And I was, of course, wondering, well, you will see it in the building, right? I mean, you will see these joints everywhere, these tenons. But this is what it is, right? And ultimately, this is the ceiling of the finished building. And I didn't find it problematic in the end. And you can tell the spacing between the plates, the thickness of this shell from looking at the joints, which is kind of interesting. Behind it is technology that we play with, and it's great to see from Gianni when he was already working with AutoLisp. These methods, they've been there for a long time, and you don't even need a very fast computer to do these kinds of things. And it's amazing how little you need to do incredibly complicated things if you use a computer for computation and not just as a tool that helps you to draw like we did before we had computers in architecture. I think we still need to ask ourselves sometimes the question, can we take more advantage as a designer, not just being a user of software, but really, or a user of a computer, but really something more on the developing side? Because as an architect, I think you want to develop things. You want to create not just things from a software that is completely deciding on which options you can use and which you cannot use. And it's the same with the machines. This machine that you see here, when we started the project, it was the 20-year-old machine, 20 years, and it was really on its last leg. But it was fine. I mean, it has 3 axes to turn, and it has a control system. So that is absolutely enough to do highly precise and complex geometry cutting. In this case here, there was actually some optimization needed to speed up the process because we needed to be a lot faster than we were in the lab. So a big part of the programming here was to optimize that every cut that can be made with a saw blade is going to be made with a saw blade, and then only where you need the finger cutter, where it's going to take a lot more time to process, this tool was used. And yeah, here you see an image of the building from above. It's this folded shape. It's a relatively simple shape, but it is 500 individually shaped parts, which were all processed by an algorithm. And maybe it's also interesting for you that the entire files of this project were less than 1 megabyte. I think that that's really important because today everything in architectural software is so bloated. You have gigabytes and gigabytes of files, and that sometimes makes it difficult to control your design, to control your architecture. And I think if you have a very good parametric model, you can get back a lot of control because it becomes a very simple model in its skeleton. And then when you have the model, you can experiment. So here we afterwards use the software to make some formwork for ultra high performance fiber reinforced concrete. So there's so much to play with, so much to experiment once you have these tools set up, which will take time, but then it might pay off. The Recycle Shell project was really starting from recycling, the idea of recycling the cutouts of CLT. I really believe in the last years, we've discussed a lot that we're going to have some problems with climate change, and building has a big part in it. 40% of the emissions, 10, 11% just in materials. And I believe that we can actually use digital technology to help addressing these problems. And the way we're building right now with wood is good, but it can be much improved. As you see here, this CLT, which is very popular, there are huge cutouts, and we will throw away sometimes 15, 20% of this material, which is a little bit crazy because this is expensive material. Every square meter costs a lot of money. It's a high performance material where you take all the nodes out with a computer scan, etc. You do not want to chip this and use it for heating. It's a good material, but it's also difficult to put it back together into a flat ceiling or a wall because it will have traction, and it's difficult to deal with inexpensive joinery. So the idea was that we solve this problem. We're going to have a lot of joints. We need to use inexpensive joints. So we want to do it completely with wood. And then the trick of being able to use these joints is the global geometry, which we used, and that was a shell, which is compressive. So in a compressive shell, you do not need very high performance joints because it's mostly, these masonry shells from guys like Eladio Dieste, fantastic. You have to look at it if you don't know it yet. And these shells, they don't need any joints. They have mortar in between, which can take nothing but compression. And they can span 50 meters with 8 centimeter thick masonry. So for plates, as you see here in this reference, if you work with plate elements, then there are some geometric rules, and it's mostly really that you have always these three edges meeting in one point. And then you can make a so-called constant distance offset. So you can actually give whatever form you choose, you can give it a thickness. And it will work out with the nodes. You can offset it in 3D basically. And yeah, based on that, we made some first experiments with these joints. As you see, it becomes like a huge Lego puzzle. And yeah, we were really happy. The fit was good. And with these machines, you can work highly precisely. You see there's some glue on the joints for safety, so they can't come out. But usually you wouldn't really need that. You can, if you don't, this was transported with a truck in several places, but you wouldn't really need the glue. It works on compression. And this first thing that we made, it was for a trade fair exhibition, just the first small prototype. And there were a lot of people complaining, it's sitting on 3 columns. This is not a shell. And they were right, of course, because a shell works differently. And it's impressive that this was actually not collapsing on these 3 columns. So we wanted to build a real shell. And luckily, we got a building site from the university to put this here. And we wanted to make it a little bit bigger, which brings us into the challenges of building a real shell. And if you build a real shell, then you will not have a constant curvature. You will have a catenary shaped curvature, which is the shape that will not have any bending in it. And that's what we want for the joints. But the challenge that comes from that is, and that's quite interesting, your structural optimization is kind of making your geometrical optimization or your fabrication optimization a lot more difficult. And because if you want to make these planar shapes, then constant curvature is making your life a lot more easy. If you have a curvature which is changing, and it's also, as you can see here where it's getting green, it is directional. So this means you have in one direction of the surface a different curvature than in the other. Then it means that your pattern, it needs to follow this direction. You will see if you look at these hexagons, pentagons, in the middle of the structure, they have no orientation. But then if they move into the legs, they start to have a clear orientation along the leg, along the curvature of the surface. And this is your only solution to make this from planar elements. But ultimately, it also will reflect what's going on in the structure in its visual appearance, which I find kind of interesting. So then we used programming to make some scripts to process this geometry into 3D parts. But actually these 3D parts, they have little to no importance other than looking at it, because sending it to the machine, it requires completely different data. Sending it to the structural engineering requires completely different data. So really the Rhino model was only to look at it and to see if it works out for development, for internal processes. And this is the fabrication model that's what exported in a completely different format. And this is the visual output in the fabrication software at the manufacturer site, where here you can see a simulation of that machine. And yeah, these machines, they are super efficient. So it's producing one of these elements in 5 minutes. And it was a very low cost project, actually, what we built here. We had a very, very small budget, and production was taking 1 day, and assembly was also taking 1 day. So these complex geometry projects, they do not need to be necessarily expensive, but you need to spend a lot of time for the programming, which in practice can be, of course, very difficult also to charge somebody, because there are typically some rules for how that works, and they don't really consider programming IT development work. this is also maybe an important picture because when we built this, it was very important to get the permission, and they wanted to see if we have a proof for the structural design. And structural design here, it's difficult to prove because it's difficult to calculate. And so we needed to prove it with an actual physical experiment. We loaded the structure and we compared our simulation with the actual loading. And I think the results that we got here, which were really good, they were really important. So if you ever want to build something like this, take the paper that we published, and you can absolutely use that for the next time somebody needs to get a building permission, because these results, they have been professionally taken. And if you use the same kinds of connections, then you can really take this as a reference. Yeah, and this is the final project where we actually didn't want to crush it after and dispose of it. So it was an experiment, but we also wanted to keep it there. And so we put a roof on it. Actually, one of the cheapest options for such a complex shape is a green roof. And I also found it kind of fitting in this forestry environment. So this picture here is from just a couple of months ago. It's been there over 13, 14 months during an entire winter. And I think this can really last for a long time. It's built in a way that there's no water. The water is rinsed off the structure properly. So there was actually the same amount of money that we put for the wood was for the green roof and for these details to get the water off of it. So really keeping it there was making it a lot more expensive. But the interesting part of this is the wood was really cheap. So just quickly, I think I got 5 more minutes to show this last project, which is also with a good old friend from London. Gianni probably knows Eduardo, right? He's a very good friend of mine, and this was such a great opportunity to do something together. Took a class of students, and we visited him, and together with his class of students, we built this structure using their robot, which they had there. And so again, we had a budget of, I think it was like 5,000 Australian dollars. And we had the robot and we had 40 students. So let's see what we can do with this, right? And they also were kind enough to let us build something on their terrace of this Wilkinson building in Sydney. So that was good because we could actually drill into the structure. It is an old structure which is going to be demolished in a couple of years, and we could really anchor something to it. And yeah, we took inspiration from, again, structures like Friordo's multi-hull grid shell, optimized geometry, lightweight design. I'm a huge fan of his work. How he worked with physical models is just amazing. And we have it so much easier today. And I even got to talk to him a couple of years ago, and he was amazed of the possibilities that we have. So we should really take advantage of this. And this was the idea of this exercise. Then there's one question, how to design a good shape, and the second one, of course, how to build this with 5,000 Australian dollars. So in this case, we only had very cheap plywood, and we needed to make this in a way that we can utilize the 80 helping hands, right? So we need to make it modular. So the modules are lightweight, they can be carried without a crane. Every student can take one. We can split the work in a huge group. This was a 1-week workshop, so it needs to be really, really organized. And we wanted to finish the project. The flights are booked. You don't get it done. Something doesn't work out. The project is not going to happen. So there was a lot of pressure. And yeah, here you can see how the students were in the very beginning thinking of joints, right? We make these lightweight boxes. How do we join the boxes? And the idea was really to, again, use the wedge joints, where you have the possibility to squeeze and pull things a little, which is extremely important. Things, when you put them together on site, they are not going to be exactly where you are, and it's really helping to think of that in advance, give it some possibility to squeeze something together, to push things a little. Wood is a sort of flexible material, but you need to be able to apply the right force. And then in the boxes themselves, we just make these cutouts, and the joint is always the same. And we wanted to make the joints from the waste material. So we have some cutouts, and the cutouts we can cut into strips, and the strips are going to be the joints. This is the machine we have here in the basement. And you can see that, again, it's a very simple machine, but with a little bit of Rhino script, this can cut almost any part out of a plate. And on top of that, we also made these little cuts for these plastic clip connectors, which help us with the gluing, because what really is holding together these plates is polyurethane glue. And this glue needs to be pushed together. You need to clamp it. And the sides are all at a different angle, so you can't really put a regular clamp. And the idea was that these clips, they are holding it in place, and then you are just putting a weight on top of it on the two parallel sides, and then you can glue it. So this was the first prototype, and one of the biggest fears that we had was, we are not working, imagine this as bricks, and in bricks, you usually have mortar, 1 centimeter of mortar, to take the imprecision of your bricks and to compensate that. And we do not have any mortar in between here, there's nothing. It needs to be perfectly fitting. If it doesn't perfectly fit, you're carrying on errors, you're carrying on imprecision in the second row, in the third row, it's not going to, we tried to make smaller models of it, impossible, because we didn't get the right precision, and then your problems are just adding up. But luckily, the larger you make things, the easier it gets, because the tolerance is the same and the structure is larger, so it's less problematic, which is a shame because it's so difficult to make models of these things. And yeah, it did work out with the precision after much calibration of the robot, which if you see a robot in a university, you know you have to calibrate it because it has been abused and it has been crashed. And so before you want to do anything with a robot, you need to calibrate it, and then it's going to give you good results. So after that, we were ready to go to Sydney, and we had some fantastic site visits here. This building you should definitely take a look at. This is actually not the International House, it's the second one. It's the Daramu House in, it's close to the first project from Lend-Lease Australia, these 8-9 story timber buildings. It's very cool. And yeah, here you see the robot cutting some of the plates. And also the software for cutting these plates, you can download for free on Food for Rhino, and also on my website. It's free to use software that we used here. That came out of my PhD thesis. So here you see the clips. And yeah, you can imagine we had like 40 people running around, and everybody had a job. This is the joint production station with these templates that they built. And maybe I show this little video. I'm not sure if you have the audio.
I don't think so, but at least
no audio.
We don't. I don't hear any sound. No.
But maybe I can say some words. You see here the nesting of the parts. Yeah, you see the speed. This was actually very slow, but later with the robot we could do it faster. So yes, as you see in the pictures, there was some problems with the painting where they didn't actually mix the paint before they painted. So some parts were painted different than others, but it was really a quick project. It was a 1-week project, but I still think we actually got some interesting result out of there. It was even a finalist in the Australian Timber Design Awards last year. And most importantly, this project was a lot of fun. Yeah, and every time I see it, I'm thinking I can't wait to get back to traveling and doing these kinds of projects. Maybe next time in Turkey. Can't wait until this whole COVID thing goes by. Thank you very much for your attention.
Thanks a lot, Christopher, for these very beautiful buildings you have been designing and building. And yes, why not in Turkey? Because this is my aim also, not only to make presentation, but also to create workshop with such kind of materials and very interesting design process. So please, if there is any possibility, I would be happy to do it. So now after these 2 presentations, we still have some time to for Gianni and Cristopher to answer some questions if you have, and I'm sure a lot of people have, and to kind of start a conversation about this building construction, this building process, and all these computer designed buildings that is, at least for me, a totally new world, and I'm so happy to see it. So, anyone have any question you can ask, or as I heard, Christopher, you had some question for Gianni, so maybe you can also ask him. I have also some question myself. You can use the chat or also to ask your questions.
Can I ask, teacher?
Yes, please, Batuhan.
Firstly, thank you for the presentation. All the examples were very good. Just I wanna know that these shell structures, as you said, there were not mortar like between the bricks. Also, you create a shelter. Probably these connection points were high actually. It was the problem. So how can I say? I don't know. Also, is water problem too. How you cut this flow of the water?
So there is on this shell, on all of them, basically there was a waterproofing layer on top of it. If this was my shells that you were talking about, but I guess it would be the same for Gianni. You have a waterproofing layer on top of it, and then you have your cladding, which was in his case the copper, and in my project the green roof, for example. So there are pretty much standard details for it.
Okay, thank you.
But it is, if you make a flat roof, actually with timber, if you make a flat roof, that is very bad, because there's one thing that you get your roof watertight, but there's going to be a day when it's not going to be watertight anymore. And then that day, it will matter so much what is the angle of your roof. Because if you have a steep roof, then your water is rinsing off. And then if you have a flat roof, then it won't. And
it's the big problem.
Yeah.
Exactly. Thank you. Also, as you said, there's a green roof design. Also, isn't it the problem about the water?
No, I mean, well, I mean, this building, it hasn't been there for 10 years, obviously. So it will be interesting to see what happens in 10 years. But the company that we work with there, they have a lot of experience. The company is Optigrün, if somebody wants to work with them. There's a second one, Zinco, here in Germany. And they've made for decades these types of green roofs. And again, it would be a lot more problematic if it would be a flat roof. So also the next problem would be if you have a structure below that's hidden. That's something we have a lot in modern buildings, that you do not see the wood exposed. That can also be dangerous. It cannot dry off to the inside, and you can also not see the problem coming. in the building, all of the buildings that you've seen also in the first presentation, I think you would see the issue because the structure is exposed. And that would also be very helpful.
Thank you for the answers.
Anyone else? Any more questions?
I can see one in the chat about
yes,
the distance.
I guess it's for you, Christopher.
The timber folded plates cross on the... it's 20 meter span, 20 meters without a column. And it could have been a lot more. The problem really in the theater was it's not a very good shape. You see, it's a frame. It's standing on two walls. And these two walls, they are covered by a roof. So you get a lot of horizontal force on a wall, on the top of a wall. And these walls, they were kind of folded, but they should have been folded more. They were folded at like 130 degrees or something, and they should have been folded close to 90 degrees, because then the wall becomes a lot more stiff and it can more easily take these horizontal reactions. The best thing is, of course, if you bring down the shell exactly without any kinks, right? You bring it down smoothly into the ground, where you will need a lot of concrete. Or you have some sort of wall that is, there are some buildings where they put another building on the side of it to reinforce that wall. Then there is the possibility of folding it. Or like you see in Eladio Dieste's work, they have very thick stone walls to take the horizontal forces.
Can I ask Christopher something?
Please.
Yeah, I was just wondering about what you can't build in timber. I mean, you know, what doesn't work, because
underwater.
Yeah,
I don't know.
I mean, it's an interesting question, that first one, isn't it? It's a water, anything near water, anything holding back water, but anything kind of above ground that you can keep dry.
I think the tropical setting in Costa Rica, it was certainly also challenging with the humidity levels, wasn't it?
Yeah, and it needs a lot of maintenance and care. We had problems later on because it wasn't looked after properly. But for instance, we designed a football stadium, all timber football stadium. And obviously we had roof protection to the timber, but the main issue then was fire concern with the stands themselves, whether that would be a problem exposing. We wanted obviously to expose the timber. And we didn't win the competition, so.
There has one being built in Nice by Design to Production, right? They did all the compressive elements in timber. And I think with this fire hazard, that's really a huge topic. And there has been so much more light being shed on it in the last years that there was some totally ungrounded fear about the fire safety. The problem with timber is very reliable when it burns, right? You have a certain speed at which it burns, and then the cross section is going to get smaller. And if you know what is your minimal cross section, then you will know how much time you have, or what should be the right dimension to give you the time to get the building evacuated, right?
Yeah.
The much more pressing problem would be smoke. But in a football stadium, maybe that wouldn't even be that huge of an issue.
And that would be the same for most of the material anyway, because, okay, the structure in timber might burn, but when you have a concrete building, you would have plastic or any other materials that might burn. So smoke is, for me, smoke is not the main issue of timber, because, I mean, in case of fire, other materials are also burning. Any cladding material you might have, anything might burn too. So structurally, but as you said, structurally, there are ways of designing it and calculating it. So I don't think it's so much an issue now, as this all timber skyscrapers start to be built, means that really there is reliability on timber because they are being done. So
Yeah, I'm definitely sure that what we need is not only more timber, and to come back also on that question of what you cannot do in timber. I think I don't even want to focus it purely on timber, but we need more innovation in buildings. And I see in France, for example, they put now a quota for timber in buildings. I think we should rather put a quota on innovation in buildings. To really, because I also see your projects go for a long time, over many years. You have so many obstacles to overcome, like I know too well. There's so many projects that are delayed and delayed over years, and you have so many obstacles to overcome, really. And it could be easier if there would be more incentives also for doing innovative architecture.
Yeah, I totally agree on it. And I mean, when you have, it's a question from Mehmet about the sustainability and comparing to other materials, but also that's, if all the buildings are built with timber, there's not enough timber.
Well, I read somewhere somebody saying, if all the buildings
are built with concrete, there's not enough concrete and so on. This is the same issue. Oh.
The thing is, you cannot farm concrete because it's a not renewable resource. You know, you will actually run out of sand, and it's creating huge problems in the parts, because you cannot take a sand from the desert, which a lot of people don't understand. So this is actually, and wood is something you can grow, you can farm it. And if you go to Australia, which is not a forest country, then you will see, if you drive north from Sydney, you will see huge farms where they are farming wood, and it's growing fast. And we have made a lot of progress in forestry. So these guys are very smart what they do. They can grow wood very fast. So I think we're not going to be running out of wood because we can regrow it. And currently in Germany, for example, we have a lot more wood every year growing than we are using it. And the one that we're using it for heating mostly, and for making paper and cardboard. COVID cardboard.
Yeah, and also bamboo and other materials that can be used. I mean, again, grown materials. There are a lot of new materials that are going out every day. I mean, every year at least, new possibilities with materials. So that's what is really interesting. So yeah, interesting question of Gianni about the occurs.
There is an answer. It's using a very long stick. There's a system called Reach and Wash that has water in it, and you can do it from far away and clean it.
But on the top?
Yeah, but you stand in the garden and do it, you can reach it. Okay. Yeah.
Wow.
So it's safe.
Or drones.
Also this. Yeah, I had a question for you too, Gianni, on this building. And maybe you told it and I haven't heard it, but since it is in UK, so you need some heat insulation, I guess. Where has been put? On the top of the shell then?
Yes.
Below okay.
Yeah, so on the structure we see then has another structure with insulation in between it and over it, and then plywood again for the copper.
Okay, yeah.
So,
I guess so, but I haven't heard it, so maybe I don't know. It was maybe I didn't follow everything properly, but I
thought it was an interesting point of Christopher's, is to be able to see what a building's made of, and that also shows you problems if there are any. So it's quite an interesting point there.
Yeah, we had in the VD theater, there was also insulation in between. So on top, we had the protruding joints, which we actually protruded by the same distance. So you can also put some insulation mats on top of it. But then there was also, the boxes were filled with insulation material. Okay. And that was pretty critical because you could have moisture inside the boxes and you couldn't see it. So in that case, we put a system to monitor. So you should always do that if you do a building like this. There are some 2 wires, exposed copper wires running on the top of the wood. And they are measuring the electric conductivity of the wood, which is changing with the moisture content. So if there is the moisture increasing anywhere in this line, beyond a certain value, it's going to raise an alarm. And I think this is extremely important. Building with wood is one thing, but really keeping it, maintaining it over a long time without creating huge problems and cost is just as important. A lot of people say after this timber boom that we're having right now, there's going to be timber building problem boom in 10 years.
But at the same time, we have buildings made of timber that are hundreds, centuries old, aren't they?
Absolutely.
So we know it can be done.
Absolutely.
So you mean that all the boxes are monitored permanently in your building, in the theater?
The critical ones, yes, the critical points.
Wow.
Which is you can predict where there's going to be the condensation.
Yeah. Okay. Thanks a lot. Is there any other question?
There's one there in the chat.
Hi.
How much time was there?
Okay, in your house, Gianni.
So physically on site, the main structure I showed in the video being craned in was done in 4 days. The process then of the second layer was probably another 2 months. And I'd say in the workshop, it was probably 4 months work. So if they were all next to each other, it'd be kind of 6-7 months altogether. I was amazed by Cristopher saying they did his in a day. So
yeah, me too.
We had no money. There was no money.
Yeah, but I have been leading workshop, you know, on not with timber, but with straw bale construction and other techniques like this, very small structures. But in 1 week, so much work is been, including the design, isn't it? Or not?
Yeah, it's really born out of a very tight context where you have no other chance than doing it. But I can tell you, like into developing the software to really get on these machines, which was, to my knowledge, the first time that you could access such a machine with your own code, because these machines are typically operated with a software that is not usable for the kind of geometry that we do. It's highly optimized for regular buildings, and it becomes a very closed ecosystem, which is fantastic at what it does, state-of-the-art architecture. But if you want to do, and this is bad, right? This is the same thing that I see with all of this BIM and Revit, that things become highly optimized for a certain state-of-the-art of architecture and building we have established, but it does make innovation more complicated. And I see the same thing sometimes with the younger generation, that the fantastic operating systems on touch phones, touchpads, they are making it very easy to use these computers without really understanding how they work. And it used to be in my generation that you wanted to use a computer, and if it was to play a game, you need to really understand a little bit about how the computer works. And I wish this would be more present in education in schools, which in my country it's unfortunately not so much. We need to understand what a computer can do to really utilize the possibilities in architectural design. And as you've seen in these all of these buildings shown today, it's very exciting possibilities, isn't it?
Yes, it is.
Cristopher, just on you showed a slide of taking one of the roof and then pouring in the what was it, reinforced?
Yeah, ultra high performance FRPC.
I think that is such an interesting idea, that I think it's the same with models, but also making things, is they make you think of other things you can make with them. So having done that roof, you've kind of looked at what else it could do.
And there could be so much more. There's just, please take it. Everybody who's listening, do exciting projects. Take it as inspiration. This ultra high performance stuff, it was very expensive.
Right.
And I mean, this question is making me think that behind you, Gianni, and on the last picture you showed a lot of models of buildings. So I guess you are working a lot with physical models.
Yeah.
And we have now at university this problem that since 1 year, we are not going to university at all. So our students, they don't do any physical model anymore. So what do you think about this? Just working on
to make a model,
digital models.
You need a piece of paper and a pair of scissors. That's all you need. So you don't need a workshop. You don't need a computer. You don't need a 3D printer. You can make models by hand. People have been doing it for centuries. So
yeah, but they don't. They don't.
I know they don't.
Because they are not forced to. They are not forced to, so they don't.
I've been forcing mine. They've been making models during COVID.
Yeah,
so very successfully.
I've been forcing mine as well. So we did a project during COVID where our students had to convert their bedroom into a workshop, and they had to make a structure in their bedroom.
Smart.
Reluctantly, but they did, and it's quite interesting. So we've now got these kind of pictures of bedroom workshops, which are. So I think it just takes, you know, insistence.
Yeah, I should suggest it to our coordinator of studio to make them work with physical model really, and not that has been done. So maybe it will work. Yeah. But I hope we will not have to. I hope next semester will be real.
Mm. Yeah, don't talk too much about work safety.
Okay.
But I can only support this. Please keep making models, and absolutely, out of scarcity comes creativity often, and really all of this technology can also be confusing. You can really do amazing things with a piece of paper, all of these folding things, and then for programming, you don't need expensive equipment. You can do this with any computer.
Okay. So I guess with this nice thoughts on still you guys that are fully working on computer design, but still working with models, I'm really happy to hear that this is also a way of making architecture, even if you are using the computer to help on the design and the definition of the pieces that needs to be produced. Working with physical model is still one of the way of designing. I'm really happy to hear it, and I guess we can finish this presentation on this nice talk. Thanks a lot, really a lot for this project and this presentation, and I really hope we would be able to do something together in the future as a workshop or more detailed presentation on how to use computer to design timber building. So thanks a lot again for all of it.
Okay, thank you.
Thank you for the invitation.
Good luck. Thank you.
Okay, have a good evening. Bye-bye.
You too. Bye-bye.
Bye-bye.